Hi, so in this video we're going to continue our discussion about pi nucleophiles. We've already covered the first page of the outline from this section. What we're going to be covering specifically in this particular video is the general mechanism addition of alkenes with X2 type electrophiles, where X can be chlorine, bromine, or iodine. In terms of the general mechanism, notice that we're adding an alkene and some species X2, Br2 in this case. The first part of the mechanism is to know that as a nucleophile, whether it's charged or not, as it approaches a halogen, while there was no dipole originally in the halogen, the approach of the nucleophile pushes electron density towards the far side of the Br2. That creates a slight delta plus on the closest Br2. So now this nucleophile will be attracted towards this end, the delta positive end of the bromine electrophile. So the first step of the reaction, the alkene is attracted to the bromine, which forces the bromine-bromine bond to break. Now there's one different thing from the previous mechanisms that we've seen. For example, if this was H with some leaving group, and that's that a lone pair on the bromine can come back towards the alkenyl carbons and form a bond with one of the carbons. What that makes is what's known as a bromonium, or halonium if it's another halogen, intermediate. The bromonium is a three-membered ring that has a bromine in it and that has a formal charge of +1. Notice the bromine has to add both these bonds to the same side of the original molecule. The next step of the reaction is a nucleophilic attack, and that attack is going to come from the back side of the molecule. So with the bromine pointing up, the nucleophile, in this case the other bromine, it will come in from the back. So this bromide comes in from the back, and that carbon-bromine bond breaks from the front. So there are two steps to the reactions of an alkene with a halide. The first step is reaction of the alkene with that halide, displacing the second one. Lone pair on that first halogen comes back. The second step is the attack of the bromide to one of the carbons from the bromonium intermediate, and that forces the carbon-bromine bond to break. The nucleophile comes in on the opposite side of that breaking bond, or anti to it, and we're going to discuss that idea in more detail in the next few slides. In terms of the orbitals involved in the reaction, the pi orbital, which is filled, is the HOMO, or highest occupied molecular orbital. It's going to be attracted to the LUMO, the lowest unoccupied molecular orbital of X2, which is the sigma star orbital. When those two orbitals overlap, they form a new bond. The other overlap that's going to happen is between a p orbital on the halogen and what's going to become an empty orbital on the carbon to form the second bond. Next, when the nucleophile reacts with that halonium intermediate, the highest occupied molecular orbital on the nucleophile, which is filled, is going to overlap with the lowest unoccupied molecular orbital of the electrophile, the sigma star. So the highest occupied molecular orbital reacts with the lowest unoccupied molecular orbital to form a new bond, and there's the new bond there on the right. Because the nucleophile comes in towards the halonium from the opposite side of the halonium, but in the same plane or in line with that breaking bond, we call this anti-periplanar attack of the nucleophile. So the nucleophile enters anti-periplanar to the leaving group. Now what about the regiochemistry of the reaction? When we say regio, we're talking about the region or location of reaction. Well, the first step of the reaction is exactly the same. That is to say, we have initial attack of the alkene onto the bromine, and the lone pair on the bromine comes back to either of the carbons of that alkene. The next step is to figure out where that second bromine is going to add, so where the nucleophile is going to come in. What experimental research has shown is that the bromide, or any nucleophile, preferentially comes in at the most substituted carbon of that bromonium. That is to say, it comes in this case, at the tertiary carbon rather than at the secondary carbon. The main reason for this is that at this left-hand carbon, the more substituted carbon, we start to develop a carbocation in the transition state. And just like we saw in the last section, tertiary carbocations are more stable than secondary carbocations. So we have a lower energy transition state when the bromide comes in to the more substituted or tertiary carbon. That transition state has a lower activation energy, which leads us to this product as the major one. Now with bromide as a nucleophile, we can't actually tell the difference of where the reaction has occurred, but if we had another nucleophile, such as a solvent, like water, as the nucleophile, it would have acted as a nucleophile and we would have been able to see that it reacted at the more substituted carbon. So in terms of regiochemistry, these reactions, just like the addition of HX, give the Markovnikov product. We can also use other nucleophiles for this reaction, just as we did in the last section. Keep in mind that intramolecular reactions are faster than intermolecular reactions for the formation of 3 to 7 member rings, the types that we'll be seeing in this course. If the solvent is also nucleophilic, it will act as the nucleophile for this reaction, and very common examples would include alcohols, ROH, water, and there are some others like thiols. Notice when we do an addition to an alkene, the electrophile can add either to the top or the bottom face of the molecule. Here we've shown the bromine adding to the bottom face, forming the bromonium that faces downward, but it alternatively could have formed at the top. That eventually would have given us this alternate final product. So note that multiple stereoisomers are possible due to the planar nature of the alkene and the fact that an alkene, the pi bond, has electron density both above and below the plane of the molecule. So in summary, in this reaction, we can add halogens, Cl2, Br2, or I2, to alkenes. The Br2 in this case is the electrophile. Addition first by the alkene adding to the bromine, departure of the leaving group, and a lone pair of the bromine comes back to the carbon. That forms a bromonium intermediate. Choose the best nucleophile present. In this case, water, which would be the solvent for this reaction, acts as a nucleophile, reacts antiperiplanar to the breaking bond. If there's a choice, it will also react at the more substituted carbon of the bromonium. We almost have the final product in this case, and all that's left is a deprotonation of that oxygen to give us the neutral final product.